Exercise 1D, sums and products of functions. Today we are learning about sketching various graphs by adding, subtracting or multiplying functions. What I need to be able to do, or you need to be able to do, is to understand the concept behind the operations within a function and then know how to sketch the sum, difference and product. So just as a little activity to start with, I'd like you to sketch the graphs of y equals x, y equals 1 and y equals x plus 1 and see if there's anything interesting about it. So just pause the video and when you're ready press play and we'll go through it together. So if I start with sketching the graph of y equals x, that's just a normal linear graph that goes through the origin. And then the graph of y equals 1, that would look like this. And then if I were to go ahead and sketch y equals x plus 1, now that's a linear graph that has an y-intercept at 1. So that would be there. And it's parallel to the black line, y equals x, because it's got the same gradient. Now, I wonder if you can tell any interesting similarities between the two, in that this graph, so the red graph, is the exact same graph as the black graph, y equals x, but every y value is just moved 1 unit upwards. Now, how did we possibly get that? If you think about the two graphs that we originally had, so 0, 0, and our y-intercept was at 0, 1, if I were to add the two values of the graph of x and the graph of 1, so x plus 1, so that would be 0 plus 1, I end up with 1. And so that's where I get that point from there. Now, if I try again with this point, which would have been 1, 1 for both of the graphs, so in this case, if I were to add the two graphs together, so the y value of the black graph is 1, the y value of the green graph is 1, 1 plus 1, gives me the point here of 2. And what you can see is that all that's happened is that every y value, all we've simply done is just added 1 to it. And that is essentially the key idea of sums and products of functions. So what you're doing is you're grabbing one graph, the y values, grabbing the second graph, the y values, and then you add them together or subtract or whatever it's asking you to do. So let's get into the theory of it. So sums and products. For two functions f of x and g of x, the sum of the functions is written like this. So f plus g of x, the difference is f minus g of x, and then the product is f times g of x. So that's the notation there around it. In terms of the domain, it's quite straightforward. It's always just whatever the intersection is between the two. So it's whatever is common to both. So the domain of, you can see all of them, plus g, minus g, or times, is always just whatever they have in common between the two. That's where the new function is going to exist. So I've shown you kind of a graphical example of how it works where we add the two functions. This is what's actually happening in terms of the mathematics side of it. So you can see that here in the first column we've got all of the x values. These are the y values of f of x. So if I were to sub in x into here, whatever the values are, this is the y values I'll get out. This is the y values of g. And then when I add the two functions, all I'm literally doing is I'm going to be adding the two values together. So that will be 0 plus 5, which will give me 5, 1 plus 3, which will give me 4, and so on. So that's the overall process. That's what we're doing here. We are just going to be adding the y values, or if we're timesing, subtracting, whatever the function tells you to do, that's all you do with the y values. This is just another example, but it's a graphical example of how it works. So if our dotted functions are the two functions that we're trying to add, then the new function will be the function with the solid line. So they've given you an example with these 2 points here. So this is 2 and 3. This is 2 and negative 1. And what we're doing is we're adding the function. So the y values for this is 3 plus negative 1. That should result in 2. And that's where we get this new value from there. How do you actually go about doing it? Obviously, if you're going to add every single y value, it's going to be such a long process. So it is a little bit of an estimation game. The idea is to grab key points, plot those on, and then to kind of just join the dots. So the key points that I always recommend are the maximum and the minimum points of the functions, any intercepts, and any intersection. Now the maximum and minimum points usually will help you find the overall shape of the graph. Intercepts are really useful because the intercept, and I mean specifically x-intercepts here, what you'll notice is that the y value is going to be 0. So whenever you're adding 0 to something, it's always just going to be whatever that other value is. So it's a really easy point to put in. The intersection points are also quite good because this is where you'll notice, so y plus y, you actually just end up doubling. So you just double the distance of it. So let's go ahead and practice with this particular one. So keeping those ideas in mind. So the first thing it's actually asking you to do is not even to sketch, just to find the rule of the product of functions and to state the domain and range. And remember, to state the domain and range, all we have to do is figure out what they have in common. So to find the rule, which is the first bit that we're going to do, we're just going to multiply the two functions together. So f of g of x is equal to, so that'll be root x plus 3 times root 3 minus x. Now, if you remember, when you multiply a surd, you can just multiply the insides like this. You might notice that this is actually the difference of two squares. So if you were to write this instead as 3 minus x, I mean, you can just recognize it, you don't have to change it. So 3 plus x, x plus 3, same thing. You'll notice that this is actually the difference of two squares. So this is 9 minus x squared. And then I'm not sure if you do realize what function this is, but this is a semicircle with a radius of 3. This will help you to be able to state the range of it. But to be able to find the range, really, you just need to sketch the graph. That's going to be the easiest way to be able to do it. Okay, now let's start off with the domain, and then what we'll do is we'll move on to the next part, part B, sketch it, and then we'll come back and state the range here. Now remember, the domain is all about what is common to both. So let's consider the domain of each of them. So f of x, this is going to be a square root function that has been moved to the left by 3. So that's going to be from -3 to infinity. And then the domain of g of x, well, this is a a square root function as well. And remember, you always need to take the negative out. So it's been moved to the right by 3, but it's also been reflected in the y-axis. So it looks like this. So that'll be -infinity to 3. Now, if you can kind of figure it out in your head in terms of what that looks like, what's common to both of them, that's great. One technique that I might use sometimes is to draw a little bit of a number line and to put them both in. So for our first function, say it's in g, so that is going to be from -3 to infinity that it's valid, there. And this one in green, that will be from 3 to infinity that it's valid. So this is -3, 3, and then what's common to them is where they overlap. So you can see that it overlaps from -3 to 3 there. So that means the domain of this new function is going to be from -3 to 3 inclusive. Now, in terms of the range, the easiest way is to sketch it, and then we'll be able to come back and determine what the range of the function is going to be. Okay, so part B says find the rule of the sum of the functions, state the domain of range. Oh, actually, sorry, if we go back to this, we're not going to even sketch it. So this one just requires us to go ahead and find the range of it. So what we could do is just to sketch what the actual function will come out as. So that's just the semicircle. Sorry, I thought part B was to sketch this one, but it's addition. So this is just, as we said, a semicircle of radius 3. So we can see that the range is going to be from 0 to 3. Okay, so if you know what the function looks like, you can just draw it straight away. All right, so for part B, it's asking us for plus. So it's good that we notice it's not the exact same function. This time they want us to find the rule for the sum of functions and to state the domain and range. Now, to find the rule, we just need to add the two functions together. Now, this is where it's kind of tricky because we actually don't know what this looks like. I have no idea what this function looks like. It's not a function that you need to know. So domain's fine because remember that's about common, and we already figured that out before. So what was common was from -3 to 3. This time we actually can't find the range because we don't know what this function looks like. So in order to do this, we need to go ahead and sketch. Now for this first time, what we're going to do is we're going to draw out a bit of a table to help us to recognize what the key values are. But in future, you're going to just kind of look at the graph and be able to add the values together. But let's start off nice and simple by drawing up the table. Now I'm going to go ahead and put in some axes so I can draw this graph up. Okay, so that'll be my X and Y. And we'll go ahead and draw the two functions separate, and then we're going to draw the two functions together. So I'm going to just highlight this one in red. So remember, this is a square root function that's moved 3 to the left. So that's -3. Just to try to make it as most accurate as I can. So the more accurate it is, the better your sketch is going to be. I'm also going to find the y-intercept. So when x is 0, y is going to be √3. √3 is just a little bit under 2. So you should look something like this. Okay, now we're going to go ahead and do this with our other function. So I'll just do it in green. So this is a graph, as we said, it's moved 3 to the right and it's been reflected. So it should look symmetrical, and the y-intercept will actually be the same. So I'm just trying to get it to look as symmetrical as possible, even in terms of where we end up on the other side. So I think that that looks pretty good. It looks quite symmetrical there. Okay, we can label all of our key points. So we've got our -3, 3, our y-intercept was 3. When they are the values, so when they are 3, I'm just trying to find the endpoints now, because that will also help me. So with the green function, when x is -3, I get √6. So that'll be -3 and √6. And then I think this one will be the same idea. 3 and √6. Okay, so that's an overall idea of what my graph will look like. Now from here, the idea is to add all of the y values. So like that's 6 and 0. If I write in the proper intercept, it will help us. But just to make our life a little bit easier, I'm going to draw it up as a table. But as I said, in future, you don't need to waste your time drawing up the table. You can kind of just do it by looking at it. But let's start off with that. So if you remember, I spoke about some key points that I would always look out for. I would always look out for maximums, minimums, intercepts, and intersections. So we don't really have a maximum. We do have endpoints. So that could probably be one of your points, but you'll notice that the endpoint occurs at the same time as the intercept. So when x is -3, we have both an endpoint and a maximum of the two different graphs. And same when x is 3. And they do intersect when x is 0. So I'm going to grab these 3 key points, and then we can go ahead and plot them on. Now, it's all about the y values. So let's draw up our y values, and then we're going to add them together, and that will give me the two functions added. Okay, so when x is -3, we're looking at the red function, f of x. We're going to list out the y values, so that'll be 0, √3, √6, and then for the green function, it's just the opposite. So that's going to be, when x is -3, it is √6, √3, and 0. And now for f of plus g of x, all we have to do is literally add those two y values. So 0 plus √6 is √6, √3 plus √3 is 2 √3, then √6 plus 0 is √6. And now all I'm going to do is for these x values, I'm going to go ahead and plot these y values. So when x is -3, y will be √6. So you'll see that that'll actually be on top of that one. And that's what I meant by intercepts. When one function is an intercept, the y value is just literally on the other graph, because I'm adding the y value of this graph plus 0, which is not going to change anything. When x was 0, which was the intersection point, we end up with 2 √3. So this is double this value here. So one way you can do it is to kind of just think about the distance. So if this was the distance for √3, we just kind of want to double that up at the top. So it'll end up somewhere around here. And then finally, √6 plus 0 was √6. And then it's just a matter of joining the dots. So this is what this new function is going to look like. And so that's pretty easy now to be able to find the range for it. So the lowest value that I can see is root 6, and then the highest value that I can see is root 3. Or rather 2 root 3, sorry. Okay, so in its crux, that's how you find the sum of two functions and how you sketch it. Now, you'll see with this example here, we actually don't, we do have some y values, but we don't have a specific grid. It's a lot easier to just kind of look at the key points and add together, put in some points, and then join the dots. So I'll show you what that looks like now. So key points. First thing we talked about was maximums and minimums. So I can see that the maximum occurs at both of these points. So if I were to add these two values, 4 plus 2, that'll equal to 6. Now, say I didn't have those values, again, you can just work with distances. And I grab my ruler and I'll be like, okay, that's 1 centimeter plus 3 centimeters will give me 4 centimeters. And I'll put a point on that. But because we have our y values, we can kind of think about it mathematically. So 4 plus 2 is 6. I might use black on this one. So add the two distances up. That'll end up somewhere up here. The next thing we spoke about was intercepts, because while this function is 0, this other function is whatever that y value is. Now, I don't know what it is. It doesn't matter because it's just 0 plus whatever that point is. So it's always going to land on this graph here, and that'll be the same on the other side. The last thing we spoke about was the intersection points, because that's simply doubling. So if this is the distance, again, I don't know the exact y value, but it doesn't matter. If this is the height of it, just double it, okay? Because it's this y value plus this y value. You know, you can estimate it to be at 1. 1 plus 1 will give you 2, whatever it might be. So the point is, I'm just going to double that distance, and it'll end up there. Okay, now the other thing we should think about is the long-term behavior. So this is becoming super negative and this is approaching 0. So think of a really negative number plus basically 0. It's not going to make much of a difference. So these values here are going to be negligible, and we're going to kind of follow this graph here because that's going to have the larger value. So now it's just a matter of connecting the dots. So it's just going to kind of look like a parabola. All right, so just try and draw it to the best of your ability, like that. And that's what it's going to look like. Now, it's never going to be perfect. Even when you look at the answers at the back of the book, it's never going to be exactly the same, and that's okay. The idea is that you're just giving an overall shape. Now, it's very rare that these questions are on an exam. I think I've only seen it one time, and in that case, you were given a grid and you could be super, super precise, like as precise as we were with this one. So in your textbook, it is going to be a little bit of estimation, but just be assured that in the exam, you're going to be given a lot more direction on how to, or a lot more support to make sure that it's perfect. Okay, last example for this exercise. So this is an exam question. So it's not exactly about the idea of sketching, but it still has something to do with your sums and products. So we're adding two functions. And what we're trying to do here is, it's a bit of a show that question. We're just trying to prove that this side is equal to this side. So it says g of x is equal to x squared. Show that. And what we will do is we will work with, it's actually the left-hand side. We'll start at the left-hand side and we need to get to the right-hand side. Or you can start with the right and get to the left. It doesn't really matter which direction, as long as you start with one of them. I always like to start with the more complicated side. So this one looks more complicated to me, so that's where we're going to start. All right, so g of u plus v means that I'm going to start writing the function of g, and wherever I see x, I'm going to substitute u plus v, and I can see x straight away. So that'll be u plus v squared plus, now it's u minus v. So u minus v squared, and we can go ahead and expand that. And we can cancel out anything that we can. So that's 2uv minus 2uv. And so what you'll notice is we're left with 2u squared plus 2v squared, which is very nice. It's starting to look like this. Now, u squared is simply just like that. Instead of x squared, it's just u squared, which means that would be g of u. Likewise, v squared would just be g of v. So that would be 2g of u plus 2 g of v. And then what we can do is just pull out that 2 and you'll notice it's exactly the same as what they want, so we can write as required. Okay, best of luck with this exercise. Remember, it doesn't have to be a precise kind of thing. Start off simple with your table and rulers, and then slowly, once you get the hang of it, you can kind of start estimating. But as long as you remember, just add the y values or multiply as the question asks you, and you will be fine. All right, see you next time.